formalism for quantum gravity. The first of our igniter of discussion is somebody who embodies something that is complicated to me to understand, because I know entanglement between two places, but entanglement between three different locations is something different to explain, so between four. So Carlo is professor at Aix-Marseille, but also a member of the Adamantia Institute here, and also a visiting professor at Perimeter Institute. So all the three nodes of QISS together.
Thank you. I'm not going to argue about anything. I just explain why I'm right. Yeah. Thank you. And actually, the title of this session is not what is the best formalism of quantum gravity. Actually, the title is do we have available general formulas for quantum gravity? What they are. And I think the good attitude is not what is the best one, is which one they are, how can we use them. Maybe I can take this away because I feel silly after a while. Okay. And I'm going to talk about that, and I'm going to talk about quantum gravity, because I think that there are theories of quantum gravity. So the idea that we don't know anything about quantum gravity is wrong. We're not sure these are the right theories. Is it sound good? Somebody? Does it sound okay? Closer. Huh? Talk louder. Okay, I'll try. I think there are theories of quantum gravity which exist. They might be incomplete, they might be wrong, but they're there. And so when talking about what is the possible structure of a theory quantum gravity can have, besides speculating abstractly what it could be, there are theories out there. And I think this is a fact. Whether they are right or wrong, complete or incomplete is a different. And I want to talk in particular about loop quantum gravity, and now this is my own opinion. This is by far the best theory of quantum gravity we have on the table. And this is the theory. And I'm not going to talk about the theory in the sense of its mathematical structure in any sense. I'm not going to commenting about this. Oops, I did something wrong, presumably. If you can take this away, it's better. But what I'm going to do is tell you what is the general structure of this theory, how it talks about what is space and what is time. Thank you very much, Matteo. I'm going to tell you what is the general structure, how to, what is space and what is time in this context. And essentially, here, the only thing to remark is that the theory is defined in terms of this triple, which is a Hilbert space, K, an observable algebra, A, and a bra on this Hilbert space, which define the transition amplitude. So there are some states, and there are some operators, and there is transition amplitudes that sort of connect the states in some way. And the question is, how is this connected to quantum gravity, and to gravity, to quantum, and how? And the idea on which the theory is based is that what we want is a quantum theory whose classical limit is general relativity. So this is a sort of well-defined question. Is there a quantum theory, standard quantum theory? As Ling Chin commented this morning, I don't see any compelling reason for changing quantum theory today. I mean, if people want to explore alternatives, fantastic, but I don't see why for quantum gravity we should change quantum mechanics, and I don't see why for one should change general relativity either. I don't think the fact is non-normalizable is a good enough reason. But of course, you have to adapt quantum mechanics to be consistent with what we learn about general relativity, and adapt general relativity to be consistent with what we learn with quantum mechanics. And of course, I'll focus on the first part. And referring to what Alex, the way Alex presented things, adapting quantum mechanics, it's a semantic thing. Are you changing quantum mechanics, or are you manipulating it so that it is adapted to general relativity. Whether you want to call this change in quantum mechanics, which I prefer not to do, or call it turn around quantum mechanics in a way which is compatible with general relativity, which is the way I prefer to do, is just an issue of work. All right. So the problem, of course, is space and time. Just because, you know, quantum mechanics, you have the Schrödinger equation, d over dt, and this d over dt makes no sense in general relativity. So let me talk about space and time. The same thing happened with space. Let me talk about space. And I think a lot of confusion is grounded on the fact that we confuse two notions of space. If to use the language that Nick, the sort of functional way of thinking that Nick recommended to us, is what does space-time do? It does two things for us. Or if you want to read the first chapter of Principia of Newton, it does two definitions of space, okay? Or go back to philosophy and look at the various definitions of space. There are two different kinds, which is not one right, one wrong. Just two different things, two different senses in which you use space. One is just to localize things with respect to other things. Where is Carlo? Carlo is next to the table. Okay, that's the definition. That's the way you think about space, and you define space in everyday language. Where are we? We are in London. It's a localization with respect to other stuff related to other stuff. As well, in the traditional Western philosophy, all the way to Newton, from Aristotle to Descartes, that's what space is, how things are attached to one another. But then, of course, we learn at school a completely different way of thinking space. Space is something which is there, which has some property which serves us to talk about distances, areas, geometry, and we can use Cartesian coordinates, which capture distance, and so on and so forth. And this is essential for doing physics because that's how Newton could define acceleration and write it here. But then, and that is the basic two different conceptual notion of space until a century ago when Einstein proposed a reinterpretation of Newtonian space as the configuration in some limit of a stuff which is a gravitational field. And the point I want to stress is that this is a profound rethinking of this notion of space, but doesn't absolutely nothing at the other notion of space. So what does space do? It localizes things in classical mechanics, in everyday life, in general relativity classical, in quantum gravity. I see no reason to change this. But what does define distance and so on is something else. It's not this Newtonian space. It's a stuff which is a gravitational field. So what does a meter measure? A component of the gravitational field. Okay? And so back to quantum gravity, in the Hilbert space, the algebra operator, a choice of operators in this algebra can be diagonalized and find a basis. This is a spin network basis. And the spin network basis has a nice property of having a connectivity structure, which of course gets from the algebra operators, which says who is next to who of these things, which those who you know something about quantum gravity can be thought as a quantum space, these dots, which are next to one another in the structure of the theory. So the localization of things with respect to one another is in the structure of the theory itself. It's written in the operator algebra theory. And if you couple this with fermions, say, which is perfectly possible, an electron, quantum excitation of an electron field, an electron is going to sit in here or here or here. So being localized. Where? In space? No, localized with respect to the other quantum gravity. Now, this is kinematics. What about time? 15 minutes of time has to be immediately done fast here. Now, same argument goes through time. Instead of thinking of a Newtonian evolution, a time in a given external Newtonian evolution, evolution external time, general relativity forces us to talk about time relationally for the very simple reason that there's all the observable time in general relativity are clock time. There are many clock times. There's no preferred clock time. So I have two events. What is the time between the two? I have two clocks. I throw one up, I catch, and the two clocks measure different lapses between the same two events. Which one is shorter? One goes up. special relativity, this is so there isn't a time among the observables. There are many times. How to deal with that? Well, the answer is that, and Alex gave you in his presentation a very nice condensated way of, so I'm repeating what he's going to say, is to view evolution, not, this is as a single degrees of freedom classical evolution. You think about the solution equation of motion as the position of x at time t, given the information you have that time t0, the initial position was x0, and of course you need also the initial velocity or momentum, just t0. If instead of thinking this way, okay, the same information you express in this way, you have a constraint between initial time, position, and velocity, and final time, position, and velocity, of course you have the same amount of information, but now you're viewing your t variable on the same footing of the other variables, and that's what you have to do necessarily to do general relativity in the language of mechanics, even classically, okay? Do we have a language for doing that? Yes, of course. In classical mechanics, the Hamilton-Jacobi formalism, when you use the Hamilton function as your main tool for doing mechanics, is already in that language. It's a function of x and t, so extended coordinate space, and x0, t0, and it satisfies the Hamilton-Jacobi equation, which is can be written as an operator acting on it. And not surprisingly, this can be seen as the classical limit of quantum theory. So can we do the same in quantum theory? Yes, we can. And it's the first step. And the best way of doing this, for reasons I'll say in a moment, is in two steps. Let me go the first step. The first step is to consider time all the time, all the variables, all the clock variables in the theory on the same ground as the position variables, and view the transition amplitudes, which are the thing quantum theory talks about, not in this way. Eigenstate of position, evolution in time, eigenstate of position, but rather in this way. You extend the Hilbert space to a extended Hilbert space, that's the way it's called, which is generated by the algebra of both x and t operators, and you view the dynamics as something that relates eigenstate up there, where P is a projector on the solution of the Schrödinger equation, which is this equation here. And you just reformulate the standard quantum mechanics, it's exactly the same transition amplitudes, just you view them in a way which x and t on the same ground. And this can be done cleanly. You can clean up infinities, position, everything. And that's the first step. The second step is extremely convenient when you do quantum gravity, not to have an initial extended Hilbert space and a final one, but to bring them together as a boundary extended Hilbert space, okay? And rewrite this transition amplitude here as a single bra on the space of, on the space here, on the boundary Hilbert space. Exactly, you can do that. And once you have this structure is for a single non-relativistic, but this structure is good enough that you can bring it up to general relativistic case, to quantum gravity, and it works. It works perfectly. There's no mystery anymore. And of course, you have a Wieland equation instead of Schrödinger. Okay? So what you get is the quantum gravity, loop quantum gravity structure. This is extended in the space, okay? And this is the W, which is the bra on the standard Hilbert space. Good. So what is this describing? That's the last key conceptual point of this super brief talk. In quantum mechanics, we are describing how things affect something else. So whatever you think about quantum mechanics, any interpretation you use one way or the other, you always are describing something acting on something else. You always have this Heisenberg cat between the quantum process and the measuring apparatus, the observer, whatever you want. Any other arbitrary system, if you are in relational quantum mechanics, your consciousness, if you are a believer in God or whatever. So this Heisenberg cat is essential for talking about quantum mechanics. I don't know otherwise what the transition amplitudes are. The probability of what? The probability of what happens at the Heisenberg. And I don't, therefore, it's going to be essential also for in quantum gravity, because quantum gravity is a piece of quantum mechanics. Now, in general relativity, whenever you measure something, you're interacting with something, you're forced to be next to it. And in fact, the only way I think you can generically think about general relativity without assuming that there is phi plus, phi minus, ADS, negative cosmological constant, and assuming extra structure beside what the theory is giving you, is to think, I think classically, that you're describing what happened in a region. So if in this region the classical approximations does not work, this is quantum gravity. You're integrating all possible space-time, causal structure, all possible dragons happening there. Okay? So the boundary Hilbert space describe what happened on the boundary, so how you interact with the boundary, and the amplitude gives you the probabilities for this to happen. Of course, you have to work out clearly how to define probability, but this is all. This is an example in which, just to say I'm not talking about the sex of angels, a black hole enters in a quantum gravity region. There is a transition amplitude, can be described quantum mechanically. Around the classical approximation is good. The transition amplitude can be computed in loop quantum gravity, and then a lot of graduate students become crazy trying to measure, to compute this integrals on SL to C and put it numerically and so on and so forth. Good. So that's my last slide to conclude. First of all, there is a way of thinking conceptually of a quantum theory of gravity. I'm not saying it's the only one, I'm not saying it's the right theory. There is one. So we can, instead of talking abstractly, how could we think about quantum gravity, consider this possible gravity. No preferred time variable, there's no evolution of preferred time variable, no arrow of time, there's no container space, there's no x in the fundamental equation, there's no t in the fundamental equation, nothing like that. What space does? Well, the quanta of space of loop quantum gravity determine relative localization, so it does exactly the job that we heard from Nick. Space is what we call space. This is what it does, and it also does completely different things, which determines areas and volumes, because this is what the gravitational field does. So the title was "What are the available general forms of quantum gravity?" This is one. It's written in terms of boundary state and amplitudes. I think we'll learn more about Adamantia in a moment. We have boundary states and amplitude with no arrow of time, and I connect what Lucian again were talking about. There's a way of formulating quantum mechanics, where you want to call it essential or not, just in my opinion, semantic, which doesn't require it. You also talk about relative facts, because you're not making a list of what happened. If I'm interacting with something, then I'm interacting with something next, and that's what the theory is about. And the dynamics is in the correlation, is the way Alex described, and is the way Hakim hinted this morning.
Thank you. Thank you, Carlo. And the next igniter of discussions is Laurent Freidel from Perimeter Institute.
Okay, thank you. It's really a pleasure to be here, part of this conference and this community. And the format is really pleasing. So, it's really a challenging endeavor to try to, can you hear me? To try to talk about, your perspective on quantum gravity in 15 minutes. We have worked on it for 30 years. So I'm going to give my perspective on it. But before telling you what I think we should do, I think it's always important to think about what are really the fundamental questions you want to answer, because that's going to determine your framework and what you want to solve, and maybe the discussion. So here is the one which I think are the fundamental questions, is the one that are driving my reflection. So the first and foremost fundamental question, if you're a quantum gravitist, in my view, is that you should worry, or I worry about what are the fundamental degrees of freedom. For people who know me, I always, often say, wait, what's the point? Yeah. What's the quantum point? So there's three fundamental questions. The one is about the fundamental degrees of freedom. Sometimes you can say, well, what is this geometrical entropy counting? That's another simpler way of asking the same question. A second fundamental question for me is, how do you reconcile Laurent symmetry with, the presence of a fundamental UV scale, fundamental length scale? And the third one is, what is quantum gravity phenomenology? Quantum gravity, in my view, is going to be a scientific revolution. It's going to come up with completely new observations. We just have to break through. Now, as Carlo was saying, you know, it's not like we have nothing. There's many amazing progress and insights in the past 20 years. We have a deep and much better understanding of how UV completions enters and what is the role of the Planck length. But there's still a fragmented understanding. So when Flaminia sent me an email and says, okay, you should talk about what are the available quantum formalism for gravity, for quantum gravity, the one thing that came to mind is a parable that is 2,500 years old. It's the parable of the 6 blind men and the elephant. And so when I think about what are the quantum formalism of quantum gravity, this is really what's happening. So this parable, as I say, is starting 5th century before BC in the Hinduism. It has many instantiation in Buddhism, especially in the Eastern world. It only made it really real in the Western world, strangely enough, in the 20th century, early 1900. And if you think about history, it would have been nice that the Jesuits knew about this parable before colonizing the world. But that's how history is there. So as you say, it's a parable of what? It's a parable about truth. There was talks about truth and objective facts and relative facts. So there are 6 blind men that are asked to tell, to understand what the elephant is, and all they do, they can touch only parts of it. So what they have access to their perspectival truth. And they end up with a perspective which are almost incompatible from one to another. And then in the main instantiation of history, it's interesting that there's many different instantiations. It's either end up in a war where nobody can agree with anything. A few of the time they collaborate to kind of get the global picture. In one history, there's just somebody that just see the elephant and tell them what to do. So I hope, so of course the metaphor here is that the elephant is quantum gravity. The blind men are the theoretical physicists with their different model, which I'm going to mention some of them. Carlo mentioned one, and there are others. And what I want to propose is a way to kind of go beyond that. And in fact, I want this talk to be for the young generation. So that is, you're going to design quantum gravity. I hope we can go beyond how we resolve this blind man and elephant situation about quantum gravity. But there's 2 things to appreciate about that. On one hand, when you look at the picture, it's totally silly to say that the elephant is a wall or the elephant is a rope. Okay? But on the other hand, it's not wrong. Okay, so there's this tension that it's completely silly, and often it's impossible for the person entangled in that perspective to realize that. But it's also, the reason it's so hard is that whatever is saying is the truth. So what we have to do is not completely dismiss this perspectival truth. Is we have to accept that they carry some truth and find out, what is the common truth. And this is the purpose of my talk, and this is really the purpose of my work and my perspective here. So what are these different perspectives? I selected 4, I could have selected 6, but it's only 15 minutes. So the first one, the most popular one, would be particle physics perspective. Quantum gravity is all and only about exchange of energy and momenta, period. And it's about a conservation law, conservation of energy and momenta, local conservation of energy and momenta. Okay, and then in that picture, what is the Planck length? What is UV completeness? Is just the fact that the 2 point center of mass scattering is exponentially suppressed at high energy, black hole form that disappears, not part of the phase space. Okay. Second perspective, ADS-CFT perspective. We heard about that. Quantum gravity is fundamentally holographic. It's all in the boundary, and the boundary is a CFT period. It's not gravitational. Okay, that's a big part of it. Then a third one, and there UV completeness is built into the fact that the entropy is finite. Okay? So third perspective is everything, the quantum informational perspective. Quantum space is only, and it's all about entanglement. Okay? And we heard about that this morning. And then there's the LQG perspective that we just heard about, which is quantum gravity is all about geometry, and especially something like the quantized area flux. Okay, and the UV completeness there is encoded into the area discreteness. Okay, so of course, when you hear that, you want to hear, some questions are, why holography? Because holography means that there's a fundamental type of non-locality in quantum gravity, and we heard that in some of the discussion, then, you know, it's nice to talk about entanglement, but entanglement is like vanilla. It doesn't describe anything, it describes everything. So what type of entanglement is specific to the gravitational nature of space-time? And then essentially, how do we reconcile this picture that it's all about geometry or it's all about momenta? You know, do we have to decide? So the centrality of area and geometry in LQG with the centrality of energy momentum in particle physics, let's say. So as usual, you know, the resolution is just to let go of the whole. You know, what makes it really difficult to have these discussions usually is when people just try to extend their perspective to the entirety of the elephant. And if we let go of that, I think there's a pathway where quantum gravity is all of these things. Okay, and so what I want to propose is this local holography, which is a synthesis where each perspective reinforces the other one instead of excluding it, which is the standard status. And here I want to be a radical conservative. That is, this new understanding or this recent understanding is really based on a deep, renewed understanding of classical GR in the context of canonical GR. And there's been a lot of technical work that allow us to have this discussion now. And it's based on asking different type of questions, or new type of questions, which is, the first one is, what is the nature of entanglement across subregions? We heard this morning that space is one, for instance, the universe is one. But, you know, I think if you want to understand quantum gravity, you have to understand how is it that, you know, there's many subsystems in this room, and what happens when I decompose my space into subsystems. And I want to be able to do that in such a way that I do it so cleanly, theoretically, that when I cut upon the thing, I keep all the degrees of freedom so I can glue it back. That's the challenge. That's where we are. Now we understand space so well that, you know, if you want to understand what is the degrees of freedom of something, you would break it up and look inside. So we do that with space, and that's this question. How do we decompose the gravitational system into subsystems, and that gives us the answer to what is the nature of entanglement. And in fact, one thing which is surprising maybe at this stage is that we talked about some kind of symmetry principle. Here, GR is based on gauge principle and particle physics based on conservation of energy momenta. So there's some kind of symmetry principle at play. And here we think that the unifying picture that can unify these different perspectives on the elephant is really the notion that there is symmetries in gravity. So how does that work? So let's start with this notion of holography. So essentially, holography is simply, what is holography? Holography is simply the expression of the gravitational Gauss law. With the gravitational Gauss law, it means that if you put any mass there, let's do it in Newtonian case, then, you know, put a mass in the center of a region, it carries flux lines that will determine the total mass contained there as a boundary integral. So you put a mass inside a region, and it turns out that there's measurements you can do never entering that region that will determine this mass. Okay, so now it is true for the mass, but it's much deeper than that. It's true for all the multiple moments of the mass. So it's not really about the mass, it's about this MLM where you take you know, you convolute what I call the mass aspect. So the mass aspect is somehow like the transverse projection of what mass is contained in that direction, you know, along my observational sphere. Yeah. So, sorry. So it's true for all the multiple moments. And as we know, if we're in the Newtonian potential, if you know all the multiple moments of the Newtonian potential, that is, you're only living on the boundary, you know the Newtonian potential. There's a property of non-screening in gravity. In QD, there's something similar, except that you can create the invisibility cloak but because you have negative and positive charge, but not in gravity. So in some sense, what it's saying is that if I define the notion of gravitational state of a system as being static states of the system, I can observe them and register them purely from the boundary. Now, okay, this is just about Newton, but what about GR? So I can think of Newton as being simply the static subsector of GR, the sector of static solution, and we'll have the same multiple charges. Okay, the difference is that the Newtonian potential will curve the metric. Okay, so that's where GR will enter. Now, how do we enter the time evolution? So if I think in this setting that quantum states are really kind of state of no evolution, and I think of motion as evolution transition between states, which is literally speaking how Born and Schrödinger and Jordan discovered quantum mechanics. They went from, you know, understanding static motion at states and and the matrix element as transitions between states. So in this perspective, what we do is that we think of the time evolution as some kind of evolution for these multiple moments, transitions for these multiple moments. And in quantum gravity, this transition between these multiple moments, the conservation law tells you that you have to emit radiation. So radiation can be encoded into also how these charges kind of evolve. Okay, so now what has happened in the past 5 years is that this is Newton, this was known a long time ago. What we now understand is what is the gravitational Gar's law for full GR. Okay, and there's a collection of a lot of people that have contributed to that. It's very technical. I'm jumping just to the result. So if you work in full GR, it's the same thing. You are going to have a notion of holography where you can measure the states of your system inside that box from measuring this boundary charge. And this boundary charge is associated with boundary charge aspects, objects with densities on the boundary. And there will be, okay, there will be the one we talked about, like the Newtonian component, okay, which is ELM. There will be a part which is angular momenta. There will be a new part which is somehow a Weyl symmetry transformation. Now, what's happening, where gravity is very different from Newtonian cases, that this algebra is non-commutative. And in fact, it's kind of a generalization of the Poincaré algebra, but it's a local generalization of the Poincaré algebra. So this object generates what people call supertranslation, the translation which depends on the position on the sphere, a different transition. Then this one generates what's called superboost, which are essentially kind of generalizations of diffeomorphism. So you can just do local boost in points of the sphere. And this one generates local Weyl transformation, so kind of a radial motion of the sphere looks on the sphere as Weyl transformation. And this generalized Poincaré algebra is connected to what people call the BMS algebra, but I'm talking about finite distance. So somehow what's beautiful is that the symmetry algebra is completely robust, whether you're at finite or infinite distance, symmetries of gravity do not change. The algebra is still the same. What's remarkable is that you have a fundamental analogy where this algebra is absolutely similar, identical, in fact, or isomorphic, let me say, to the symmetry algebra of a boundary fluid. So if you imagine that this boundary is a fluid, and it's a perfect fluid, it will have a symmetry algebra, it is barotropic, and it has a density, it will have exactly the same symmetry algebra. So I can think somehow as this fluid as being kind of the flux line that are piercing these spheres, and the dynamics of GR are going to be fluid motions on this boundary. In this analogy, okay, we can finally reconcile maybe the particle physics perspective and the LQG perspective. Remember, particle physics says it's all about conservations and energy and momenta. And of course, that's what Newton tells us. It's energy, and this one is momenta. But Loops tells us, no, it's all about geometry and area element. And it turns out that this charge, the Weyl charge aspect is the area element. So it's measuring the density of charge. And in the fluid picture, it's essential because this area element is the density of the fluid. And of course, you cannot construct a fluid, or you cannot have a constituent if it doesn't have a density. So the symmetry algebra naturally unify these two inconciliable perspectives there. Now, okay, that's what I'm saying. It plays all of you. Now, what do? We have the algebra. Okay, the states of the quantum gravitational states of the systems are just representations of this algebra. And, you need to be able to represent them. What you find is that such algebra, it's been known, since Landau, but there's even new results about it, is that they're classified by kind of two kinds of Casimirs. One is the density of the fluid, as we know, and this density of the fluid, if I go back to the talk of Martin, can be either continuous, continuous or discrete. Okay, if it's discrete, then my fluid is made of molecules. Okay, and this molecularization corresponds exactly to the area quantization that loop gravity likes so much. But there's a second object which is quantized in a fluid, which is the vortices, and can be quantized. So it's either continuous or quantum. So fully quantum fluid is molecularized and contains quantum vortices. So there's a sense in which by looking at this symmetry algebra, so this symmetry algebra represents states of the geometry. There's a direct translation between what is the geometry and the algebra generator. This is kind of a non-logical translation, but it's perfectly under control. And then, because it's an algebra generator, we know what it represents. So we do have a direct control on what is quantum geometry. And this control, remember, it's classical, it's semi-classical. I can compute exactly the Poisson bracket, okay? And once I have a symmetry, it's easier to quantize. So let me go fast. Once you have understood these things, this symmetry algebra determines the nature of entanglement, because entanglement across subregions have to share the same value of the charges. So they have to share a common perspective on this flux line here. And as was explained this morning, what you have is that in gravity, you don't have a tensor product of subregions. You have what's called a fusion product, which means that you take a tensor product, you extend by the representation of this algebra, and you have to share the charges that this algebra carries. So this is just my summary, my 15 minutes on quantum gravity, is that there is a way to kind of reconcile this very, very different perspectival understanding of what quantum gravity is. It's just to focus on the consequence of the Noether theorem applied to gravity, which reveals the generalization of the Gauss law that explains first the fundamental holographic nature of locality, that provides the detailed descriptions of the gravitational entanglement across subregions, that provides a quantization of geometry through representation theory of corner symmetry algebra, and then something I haven't talked that can give a new picture of radiation as charge transition.
Thank you, Laurent. We now go to our Mexican QISS node with Adamantia Zampeli from Morelia.
Can you hear me? Hello. Okay, perfect. So, first, I would like to thank the organizers for this nice conference. Pardon? Okay, yes, here. Is it okay? Perfect. Okay, so I'm going to talk about the framework that is called the positive framework. I will introduce the main ideas and one specific realization of this, the general boundary formulation, which was conceived and introduced by Robert Ockle. I will motivate its relevance to both quantum gravity and quantum information communities by introducing its main ideas, principles, and some examples. So positive formalism is an abstract framework that serves as a starting point for the derivation of other known or unknown theories. In this abstract framework, there are only nodes and arbitrary connections. If we add time, direction, and then a causality principle, which I will explain, then we have three options. We get the framework of convex operational, the convex operational framework, which is corresponds to the generalized probabilistic theories. And if we add structure, if we add classical structure, we get the classical, which means the structure of the classical phase space, we get the classical theory. While if we add the structure of Hilbert spaces, we get the standard formulation of quantum theory, and this is what I have pictured here. So therefore, we can, in this framework, we can have a complete description of pure and mixed states. I mean, generalized measurements also. On the other side, if one considers the positive framework in a space-time theory in a topological sense and adds locality in the sense that it is only the nearest regions allowed to interact through their boundaries directly, then we get the general boundary formulation. And this framework is formulated in analogy to the pure state formalism. And by this I mean with Hilbert spaces and projection operators. It describes quantum field theory, for instance. Had we added, instead of quantum structure, the classical phase space, we would deal with the classical field theory. So the causality principle I'm talking about, other speakers have already mentioned it. It is the notion of causality that we include is the one, for example, that Lucien Hardy calls Pavia causality principle, and but today it was mentioned also by Pablo Arrighi. So at the left I have, it is pictured that if I perform a non-selective operation, A, and then discard the state, which means I don't know the result, it is the same as no operation was performed and then just discard the state of the system. In this case, the inner product of the initial state sigma, on which acts the operation A with the identity state E, which corresponds to the discard of the system, is equal to the inner product of the initial and final state. And this is a trace-preserving operation. So this is important for the normalization condition we usually take in quantum theory. On the right, the operation is selective, and then the state is discarded. And the inner product is, in this case, when the operation acts, is less than equal to the case that no operation was performed. And this defines a trace decreasing map. So this condition, the causality condition, is important in order that we don't have influences of future measurements in the past, and it is time symmetric, which means that if we try to invert it, it would not be satisfied. So, returning to the formalism, the main, in this framework, we represent measurements, operations, observables, but also outcomes and inputs by probes. Or when nothing exists, or nothing happens, a null probe is also defined. So we represent the probes by boxes, and for instance here, the above one represents a pointer, the right a switch, and that takes different positions, and the third a light indicator. And we also represent a physical system or its boundary conditions as interfaces, as it is depicted on the left. Interfaces between the probes. So both the probes, the space of probes and the space of the boundary conditions define partially ordered spaces. And yes, that's why they constitute a convex operational framework. So how we define probabilities in this framework? I have written an example here. So in this example, a setup probes is depicted that represent measuring devices. We have a light indicator, which is turned off on the right, it's white, a pointer, a thermometer, and a device pointing to an interval. In the left hand, we have a setup of a measuring configuration signifying the preparation. Okay. So the right-hand side is the preparation. The left-hand side is the question and the outcomes. What results? So the way that probabilities are defined are as no-ask situation, and what is fixed and not fixed. So the probability is the quotient of the question over what is already known. And for instance, here what it changes is that the light indicator changes and the pointer gives a different position. And in this probability type, this is also depicted by changing the corresponding symbols, which I'm not going to explain in this short time. Okay. So an application of this formalism can be found in the indefinite causal structures. For instance, okay, so most of you know this example, but two systems are defined such that for each party there are inputs and outcomes represented by A in, A out, B in, B out. And inside of these labs, ordinary quantum mechanics is valid, while nothing is known regarding the space-time ordering between the two. So now we consider a set of selective outcomes of Alice and another one for Bob. These sets should satisfy, so M sets in this mathematical type should satisfy the causality condition I mentioned before. But for the probe outside the space-time, which is W, this condition does not hold. Okay, so long story short, the probabilities again can be again expressed in this formalism. And now I discuss the general boundary formulation, which is historically, it was first conceived and motivated by the problem of how to define transition amplitudes in generalized local regions in quantum field theory and quantum gravity, such as spin foam models and loop quantum gravity. So usually the processes in quantum field theory are defined as follows. We have an initial Cauchy surface and the final one at minus and plus infinity response respectively. And in the middle space-time, there are we have either free evolution or interactions. So the transition amplitude in the Schrödinger representation is given by this type, which is the initial and the final state times the propagator in this interval. So in quantum gravity, one wants to compute more general transition amplitudes, and we want to consider finite regions and probably closed. So these finite regions have boundaries on which the initial and final states are defined. The generalization of this transition amplitude is okay. It can be generalized by considering by writing the initial and final state as an inner product, for example, like a tensor product. Excuse me. And that is defined on the boundary. And again, we have the propagator in this space-time region. This transition amplitude satisfies a specific composition law, which is depicted here. And on the composition and decomposition is done through, okay, the transition amplitude of between two regions is the sum of the transition amplitudes of these two regions, and where in this relation zeta is defines a complete orthonormal set on the boundary sigma and sigma bar. And again, we have a definition of probability in a similar way, where as before with the transition amplitudes as a quotient, where in this case A is a positive operator which is less or equal of S, and both are less than 1. And in this approach, we can deal with the example Carlo Rovelli also mentioned before, the black to white hole transition time, bounce time. So in this case, to deal with it, we separate the region near the horizon, which is represented by the perpendicular line, in 2 regions. So X is the classical space-time, and Q is the supposedly quantum gravity region. We have the trajectory of the observer, and we have 2 variables, the mass and the proper time. We fix the mass for this case, and we ask whether whether the time will be in some interval at some moment of time. So we define a probe inside, the null probe inside the quantum gravity region, because nothing is there, no operation happens, while we have a probe corresponding to the observer in the external region. And again, we have the probabilities where we have the null probe, and the only change between the numerator and the denominator is that the interval of the time interval of the proper time. Okay. So in another useful application of this formalism is in quantum field theory. So as we know, in quantum theory, measurements are conceived as instantaneous in a fixed space and time background, and they can be represented by projection operators. Sequential measurements do not constitute a problem to be performed. But in quantum field theory, measurements are defined in a small region of space-time. Okay, so the notion of operations are not the same in the formalism of quantum theory and quantum field theory. And moreover, the causality condition I mentioned before does not hold, because it requires that the system is discarded at the end. But in quantum field theory, usually the initial and final states are defined with respect to a specific vacuum state. So it's not clear how to formulate this in quantum field theory. And another problem is, as I said, the problem of sequential measurements, the composition of measurements. And it's only one specific case of sequential measurements that are allowed in QFT, which is only for space-like separated events. So in this, in the general boundary formulation, we have a notion of composition, and thus, in principle, it's an open problem to look whether we can solve these problems of quantum field theory, of measurements in quantum field theory. But an interesting result that comes when you bound your space-time and you look for your field modes, is that additional modes of the field, which are called evanescent, appear because of the existence of the spatial boundary. Okay, so I conclude by picturing a scheme of how what kind of theories and how it can accommodate it. This is the time evolution frameworks, and this is in space-time framework. So positive formal lattices are classical theories, and anti-lattices are quantum theories. And in between, we can have a spectrum, the spectrum of the generalized probability theories. And these are some open questions for the discussion and some further reading.
Thank you. Thank you, Adamantia. The last igniter of discussion is Wolfgang Wieland from Vienna. You have the floor.
Thank you, Francesca. Can you hear me, everybody? Yes? Great. That's the pointer? Yes. Here. Okay. Thank you. All right. So I'm really happy to be here and be again at the quantum gravity meeting live in person. I'm the last speaker of this conference, so I decided to give a kind of a bit of a synthesis of what we heard about quantum gravity in this, especially today, but in this whole week. All right, and I will focus, as the organizers asked me to do so, on loop quantum gravity and spin forms, but I will also bring in a bit about new developments about subsystems in quantum gravity. Now, I want to go, let's go back to the very first day, in fact, which is the way I read it, the way I read Regge calculus or quantum gravity in 3 dimensions is that it gives us a promise for how to construct a quantum theory of gravity, namely to take finite regions and glue them together, so to construct a non-trivial dynamical quantum space-time. The idea of Regge is to take building blocks that are locally flat. So we truncate the gravitational field in a region to locally flat geometries, but then we allow it to glue, then we take many such building blocks and we glue them together in such a way that there is curvature. So we glue them together and evaluate the Einstein-Hilbert action on such configurations. And what we find is that there is now curvature concentrated on 2-dimensional surfaces dual to these 1-dimensional edges. And what is really important here is that we end up with a theory or with a state space that is finite dimensional. So the truncation gives us a sort of cutoff that we deal with a finite dimensional mechanical system. And then we can ask, can we quantize this system? And indeed, there is a phase space for this theory, a phase space that we then are able to quantize. In 3 dimensions, the states live now on 2-dimensional boundaries, on 2-dimensional Cauchy surfaces, and the quantum states are labeled by half integers, by spins. And what we find is that geometry is quantized, so surfaces dual to these edges exhibit quantization of geometry. In fact, there's a very nice way to formulate that, basically as a system of coupled harmonic oscillators that sit at the endpoint of these edges. And then the length of edge dual to these links is just a number operator, and it's quantized in units of the fundamental Planck area. But then what about the dynamics? Well, dynamics is about evaluating the path integral, and there we go back to the action. We just evaluate the classical Einstein-Hilbert action on these geometries and do the canonical quantization. And what we find is transition amplitude. So instead of a spin network, we now have a spin form, the evolution of a spin network in time, if you wish. And just as a node of this spin network is dual to a triangle, the vertices of this time evolution of these Feynman path integrals are now dual to quantized regions in space-time, to quantized tetrahedra. And in fact, these are labeled by half integers, so they're spins. The state that sits at one of these nodes is just a Clebsch-Gordan coefficient, a 3J symbol. the state or the amplitude assigned to one of these processes is a 6J symbol that we can write as a gravitational path integral. Now, then the question is how we go further from 3 dimensions to 4 dimensions. And the general setup of this theory that we get, the framework that we will have is a situation in which we assign amplitudes to finite regions in space-time and glue more complicated quantum geometries or build more complicated quantum geometries by gluing these individual amplitudes together. And as explained in Carlo's talk, the structure of this theory, it will be as follows. So we will have now states assigned to boundaries of 4-dimensional regions in space-time. But in general, there is no reason to restrict ourselves to situations where these quantum states represent spatial initial hypersurfaces, spatial final hypersurfaces connected by some time-like or null boundaries. So a generic state in this boundary Hilbert space that is now assigned to the entire boundary of this 4-dimensional region will show entanglement between the future and past components of the boundary. Hence, there's no causal structure to begin with. Furthermore, now we have to impose constraints. In other words, we have to solve the initial data for the Einstein equations at the quantum level. And that amounts to impose the Wheeler-DeWitt equation, the constraints of general relativity, whose physical meaning is that there are just no preferred coordinates. And they tell us that, so there's a quantum constraint that is a generator, which is labeled by arbitrary vector fields psi on the boundary. And the kernel or the projector that solves this constraint will then define the transition amplitudes by just contracting a generic boundary state with this projector. Now, this seems kind of logical and straightforward, this formalism, but it's impossible not to underestimate how much of a change this is, how much of a change to how we normally think about quantum theory. And this has 2 aspects. Namely, one is how to think about probabilities and causality in this formalism, and the other is about how to understand observables. Let us consider the first issue, the first problem that also Adamantia talked about in the previous talk. So a generic state in this boundary Hilbert space will have no general causal structure. The states may be entangled between the past and future components of the boundary. So how do we make sense of transition amplitudes in this situation? Well, we have to generalize them. So we select preferred a basis corresponding to some measurements and some preparation. So some experimental preparation, and then we have some measurement outcomes. And we just do formally the same as in the Born rule. We just normalize the square of the amplitudes. But then this is very, at first, this looks very similar than the ordinary Born rule, but it's actually very different. Because now situations may arise where the Hilbert space corresponding to the preparation is has a different size than the possible measurement outcomes. In other words, it's not clear whether there is irreversibility. In other words, when we change, if we reverse the order, so we ask what is the probability to have some measurement preparation given some measurement outcomes, this may not be anymore the same thing. So this is a hint at that there is a built-in irreversibility or an error of time depending on which boundary state we choose. And this will bring me now to the second problem, or the second feature that we need to understand. And this relates to the talk of Laurent, of course. Namely, how do we now extract so quantum mechanics is not only about probabilities, it is also about observables. And we do not measure length, areas, angles directly. What we measure, for instance, in LIGO is gravitational radiation, or we measure mass, angular momentum, and these are charges. Why are they charges? Well, because diffeomorphisms are gauge symmetries. And so Noether's theorem tells us that if there is a Hamiltonian, so even if if a Hamiltonian exists, then it can only be a surface charge up to a class constraint that vanishes on shell. But in the general situation, now we are in a finite region of space-time. So the goal is to quantize finite regions of space-time. But if we then ask, is there a Hamiltonian that brings us from one such boundary to a later instance, then we have to understand what happens in between, that the system is necessarily open and can lose energy. And in other words, the Hamiltonian cannot be a generic such Hamiltonian for a generic vector field psi will not be preserved under its own flow. And this is now a challenge already at the classical level, namely how to understand dissipation on the classical phase space of a finite gravitational system. And one way to do this is to change the bracket that we use. So this is now about some new developments that I have established with a collaborator in Vienna, Victoria Kabel, a student at ICOCI. And the idea is that, well, under the usual Poisson bracket, the charge will always commute with itself. So to take into account dissipation, we have to choose the bracket. So one way to deal with dissipation in a Hamiltonian system is to choose to change the fundamental bracket. The Poisson bracket is now replaced by a dissipation bracket, by a Leibniz bracket that consists of a skew-symmetric Hamiltonian term and a symmetric term that captures the loss of energy, angular momentum, and so on due to radiation. And this comes from, is studied, for instance, in plasma physics or fluid dynamics. And this and the charge with respect to this new bracket serves then as a canonical generator on the extended phase space. And I think what an interesting problem to understand is how does this translate into the quantum formalism? How can we capture this? How can we extract dissipation and radiation from our fundamental amplitudes in finite regions of space-time? Because this will relate the quantum theory to measurements of gravitational waves, for instance. So we want to learn how, for instance, charges change as we move forward in time and radiation is emitted. So let me briefly summarize. The goal of this, or the ideas that are now being developed, and the developments are now towards understanding quantum gravity amplitudes in finite regions of space-time. And this has two implications for quantum theory, namely one, that the Born rule has to account for situations in which there is no distinction anymore between, no clear distinction anymore between past and future, where we have superpositions of the states at future and past, and then to understand how that any such system is necessarily open, that there is necessarily dissipation, and how do we understand evolution in such a system. For instance, by replacing the Schrödinger equation by a dissipative equation that takes into account the loss of energy due to the openness of the system. Yeah. So thank you very much.
So it's time to take the usual break, and we do just a quick 50 minutes because the time is tight.